Hello and welcome to this episode of the Cyclo Edition, the podcast for those looking to go above and beyond in their understanding of the organic literature. I'm Grace Latowski, and I'm joined today by Matt Gensing. Today we have two special guests on our show, Min-Soo Ju and Logan Vine, who are two of the authors on the paper that we are discussing today. This paper is titled Tunable Catalyst-Controlled Syntheses of Beta and Gamma Amino Alcohols Enabled by Silver-Catalyzed Nitrene Transfer by the group of Jennifer Schomaker, who is a professor here at University of Wisconsin-Madison. Her group focuses on design and mechanistic understanding of new reactions in total synthesis. This recent Nature Catalysis paper highlights the design of silver catalysts to achieve selective amination via nitrene transfer.
So today on the Cyclo Edition, we have some special guests joining us, Logan Vine and Min-Soo Ju from the Schomaker group. They are both authors on the paper that we're going to be going over today. So before we actually dive into the paper and some of the background of the paper, we'd like to give them a chance to kind of introduce their research and maybe introduce some nitrene chemistry in the Schomaker group in general.
Hi, thanks for having us today. I'm Min-Soo. I'm a sixth-year graduate student from the Schomaker group. My research focus has been on development of selective nitrene transfer chemistry using silver-catalysis.
Hi, I'm Logan, and my research, has a lot of it's been this paper thus far. I'm a third year, just starting off my third year, and I'm moving into some different chemistry right now with palladium, tandem, cyclization, cross-coupling reactions, but our group has been in the nitrene transfer game for quite a while.
So the paper we're covering today addresses a challenge in CH functionalization, which is site selectivity.
CH functionalization is, I think, the common term that's used is the holy grail of synthetic organic chemistry because CH bonds are ubiquitous in organic compounds, kind of the definition of what makes an organic compound. And so being able to selectively functionalize those kinds of bonds will allow you access to a lot of different structures and a lot of different functionalities where you couldn't previously achieve them. And primarily, I think late-stage functionalization can allow really easy access to analogs of bioactive molecules that can drastically change the bioactivity of said molecules. And so it's become kind of a hotbed of research in the organic chemistry world.
And Logan, you just said selectively activating CH bonds. And so a big struggle with a lot of these compounds is that they have multiple CH bonds, and they're many of them are in a very similar steric and electronic environment, and so being able to selectively functionalize one over another is a challenge that many research groups are working on these days.
Absolutely, that is the real challenge. You can't. It's hard to pick one out of however many there are, and some of them are more electronically similar, and some of them are electronically different. But depending on the kind of chemistry you want, choosing one over the other, absolutely, like you said. Huge challenge.
So this paper today presents a method to do CH functionalization to form a CN bond via a nitrene intermediate. And before we get too far into this podcast, we want to go over some of the characteristics of nitrines and what exactly this group is.
So by definition, nitrines are monovalent neutral nitrogen. It's bonded to one substituent with 4 non-bonded electrons.
And I think an analogy that you can draw that might be a little bit more relatable to people is to a carbene. And taking even one step further from that, what is a carbene, what is a nitrene, and why do they exhibit unique reactivity that you can't access using other kinds of functionalities? In organic chemistry, pretty ubiquitously is taught the octet rule. An atom is most stable when it has its full octet. It has 8 electrons. And the term octet rule definitely makes it sound a little more hard and fast than it is, because there aren't a whole lot of hard and fast rules in organic chemistry. Nitrines and carbenes are an example of this, where while maintaining a neutral state, you get a highly reactive compound. So instead of having 8 electrons, you have now 6 electrons for a carbene or for a nitrene, and so you're suboctet. This is definitely less stable than something that has a full octet, but it's not inaccessible. And because it is less stable, it allows for some really unique reactivity that you can't access otherwise. So CH functionalization is one of these things that's really hard to do because of the strength of that carbon-hydrogen bond, because of how stable that bond is. It's very challenging to directly go in and functionalize that bond, and so something highly reactive like a nitrene allows us to do that.
So like you were saying, Logan, these nitrene intermediates are highly reactive, and because of that, you can't just take a nitrene from a bottle and throw it into your reaction. Maybe you could kind of go over some of the ways that people have generated these nitrenes in the past, and then also how you guys are doing it in this paper.
Yeah, absolutely. So there are a few ways in which you can generate a nitrene, and I think the most common ones that you see are things like an azide, where you can kick off N2 to form your nitrene, or dioxazolones have become a lot more popular lately ever since Chang's science paper. And there's also, you can form N-tosyloxycarbamates or other kinds of pre-oxidized carbamates or sulfamates that will allow you to form your nitrene later on in the reaction. What we are using here is another common functionality for forming nitrenes, and those are carbamates. And a lot of our previous work has used sulfamates, and these operate fairly similarly, though they have different kinds of reactivity. You take your carbamate and you react it with a hypervalent iodine oxidant, and you end up with an aminoiodinane intermediate, which then is intercepted by the metal to form your silver nitrene or your metal nitrene, whatever that metal might be.
Looking back at the history of nitrene transfers, a lot of the early work involved rhodium. A lot of this reactivity was developed by Justin Dubois at Stanford, but your group really popularized the use of silver for these nitrene transfers. So maybe the question then is, why silver in terms of selectivity? Did you find that to be a good metal catalyst for these types of reactions?
Why silver? That's an excellent question. And silver nitrene transfer started, I think, with the He group, and Perez has also done some really wonderful work with it. Silver, I think, provides a lot of opportunity for tuning because it's a really dynamic metal in solution. It's not necessarily always staying in the same configuration depending on your ligands. And so one of our early works came when we varied the ligand to metal ratio of phenanthrene to silver to do selective CH amination or CC aziridination. What ended up happening is that when we used a 1-to-1 ligand to metal ratio, we got chemoselective aziridination as opposed to the CH functionalization that we've been talking about. However, if we increased the ligand loading to 2-to-1, we saw a complete change in the chemoselectivity. And this is just because when there's one phenanthrene solution, you have a single bidentate ligand coordinated to your silver, but when you have excess, you end up with a doubly coordinated phenanthrene silver complex. And this created a very different environment around the silver, one where the alkene was not as easy to access for aziridination, and so CH functionalization became the preferred reactivity that we saw.
We also were interested in if we can tune between a very different types of CH bond in terms of CH amidation chemistry using silver-catalysis, using sulfamate nitrene precursors. But we have found that using two equivalents of BP-type ligands would catalyze CH amidation of tertiary CH bond in competition with other activated benzylic CH bond efficiently. Whereas utilizing a TPA type ligand scaffold can selectively form a benzylic amine product in the presence of tertiary CH bond selectively. And we have reasoned that with the help of computation, we have reasoned that this is due to the TPA ligand harnessing a non-covalent interaction with the substrate, harnessing a pi-pi interaction with the ligand and the substrate to direct toward a benzylic CH site.
So essentially, we are harnessing silver's geometry and electronics to use the substrate itself as a directing group, to use the benzylic site as a directing group in a way.
And I think all of those examples that you brought up kind of lead naturally into this paper, which is really trying to do a similar thing, right? But in the case of this paper, you guys use silver's unique ability in tandem with different ligands to try to differentiate between beta and gamma hydrogens, right? So it's still a selectivity issue.
So again, it's similar in a way that we're trying to achieve a tunable and selective silver-catalyzed nitrene transfer.
One thing we've talked about is how we like silver because it's dynamic and we can manipulate the coordination environment. But with that dynamic behavior comes, dynamic behavior where you don't always have the conformation that you want that drives the reaction you want to go the way that you want it to go. So in this paper, interestingly, we're actually taking silver and really forcing it into less dynamic behavior through catalyst design and catalyst choice.
So maybe we could talk about more of the kind of design principle that you guys used to achieve the selectivity. When I was reading the paper, I found the whole linear transition state argument pretty interesting. So maybe you could kind of walk us through that.
So this is based on our own work in intermolecular silver-catalyzed nitrene transfer, as well as other groups' computational studies, that a silver-bound silver nitreno species would be in triplet electronic state or is supported by the computations. So they would behave as a silver-2 nitrene radical anion species, which in transition state during the CH abstraction event would mimic a preferred 180-degree angle between the nitrogen, hydrogen, and the carbon in the transition state.
I think just to make sure I'm understanding, when you're talking about the transition state, you're talking about the hydrogen atom transfer, right, between the nitrene nitrogen and that hydrogen that you're abstracting from the carbon. So if that is the, preferred low energy transition state, and that would give gamma selectivity, how do you design a ligand to go away from that preferred reactivity and get beta selectivity?
Right, that's a good question. So envision that a non-hindered bidentate ligands can basically direct toward the gamma CH bond from the nitrene precursor. But on the other hand, if sterically accessible ligand can give us a larger ring cyclization, which is a gamma site, on the other hand, more sterically regulated, more hindered catalyst system potentially can give us a smaller ring cyclization, select toward the beta site. So that was the principle, the idea behind it.
So to test their hypothesis, they tried a variety of different ligands where they found dimethyl box gave the best yields and selectivity for the gamma CH functionalization, and a pentapyridyl ligand gave the best yields and selectivity for the beta position. The pentapyridyl ligand is very bulky, so it makes sense that it forms a very sterically hindered metal center, while the dimethyl box ligand only ever binds once to the metal, making it very sterically accessible. To look at this ligand binding further, they use DOSI, which is a specialized NMR technique.
So to take a moment to shout out to Min Shui, who is the other, along with Min Su, first author on this paper. Namely, Min Shui was able to find evidence to support that you only have a singly coordinated dimethyl box ligand, no matter what equivalence you have of dimethyl box in there. And so you really are able to eliminate some of the variation in the steric environment by having that dimethyl functionality, or to some extent also applies to other box catalysts. They're not able to easily doubly coordinate to the silver center. If you take a look at the pentapyridyl type catalyst that we use, and then you can also take a peek at the structure of the silver pentapyridyl dimer, there is nowhere else for anything to bind. It is very encumbered in every sense of the word. And that also lends itself to a very rigid structure, which Min Shui also did recrystallize that one out.
That was before.
Before this paper, yes. But we were able to get that actual crystal structure, which is very good because putting that thing into computations does not work.
So after deciding on the two ligands that would give them selective beta nitrene transfer or gamma nitrene transfer, they were able to apply this to a number of different substrates. And so I really liked how their substrate scope was laid out because they used the same starting material, and using the dimethyl box ligand, they were able to selectively show that they functionalized the gamma position, and using the pentapyridyl ligand, they showed that they were able to selectively functionalize the beta position.
Something I think really important to highlight here is that not each one of these transformations by itself is particularly interesting. So if you take a look at like the benzylic substrate, if you do gamma activation on these benzylic substrates, that's something that's been done quite a number of times with quite a lot of metals. What is a lot more interesting is comparing that to the column on the right, where now instead of activating the gamma site, we're activating the beta site, because there is a pretty big difference in bond association energy, and we're switching away from conventional selectivity using these ligand scaffolds that we've designed. And I think that is the really important thing to highlight, is tunability away from these activated sites. And this applies not only to benzylic, which is a quite activated CH bond, but it's also applying to allylic sites, and it's applying to alkyl sites. And to clarify what I mean there, tertiary CH bonds are a lot more reactive than a secondary CH bond. And with conventional methods, you end up activating, whether it's in the beta or gamma position, typically you'll see activation of the tertiary CH bond. And we are pretty effectively able to tune away from any kind of preference like that.
I think we also were able to demonstrate that our silver-catalyzed systems are capable of activating primary CH bond, which is the toughest CH bonds of all. You can functionalize in nitrogen transfer chemistry, albeit lower yield with the dimethyl box system, but we were able to achieve the primary CH bond amidation. So we try to utilize this chemistry in natural products and other types of biologically active compound derivatization. And we were able to demonstrate the tunability with these more complex systems. And we also were able to demonstrate the direct ring opening of these cyclic carbamates were possible. So they were removed pretty efficiently by refluxing in 1,3-diamino propane, generating either gamma or beta amino alcohol in a tunable and efficient manner, starting from the alcohol precursor.
And I think that leads a little bit into the real purpose of the paper is, while oxazolidinones and oxazinones can have some interesting properties in terms of their biological activity, it's kind of interesting to read up on. But really what we're gunning for here are amino alcohols. We're shooting for amino alcohols to be accessed in a selective way, and ideally in the future enantioselectively.
So looking at the mechanism of nitrene transfer here, when I first came into this, I had no idea what mechanisms were even available for nitrene transfer. So I actually went back and read the collaboration that you guys did with John Barry. And kind of my understanding, you guys can comment on this, is that there are kind of three possible mechanisms that could go on here. The first being a concerted nitrene transfer, basically, where there's a three-membered ring transition state between carbon, nitrogen, and hydrogen. Two other distinct possible mechanistic scenarios where there's a hydrogen atom transfer from the carbon-hydrogen bond to the nitrogen. And then the two distinctions between those two mechanisms, one where you can actually observe radical intermediates, and one where there's just a barrierless transition state to product.
So with the understanding of the three common mechanisms of nitrene transfers, what do you believe is going on in this system?
Well, a lot of that information actually comes from previous work done by our group at the Barry Group. That's a paper that Matt mentioned earlier. And really, it comes down to the nature of that metal nitrene species. So what the computations showed, because a lot of this was discerned computationally, and we'll get into why that is in just a second. The computations show that the silver nitrene exists in the triplet state as opposed to the singlet state. Contrast to this would be to think about rhodium. So rhodium, another common nitrene transfer metal, does have that singlet state rhodium nitrene species and can undergo concerted CH functionalization. For us, with the triplet nitrene species, we do not have the empty orbitals necessary to undergo that three-membered nitrogen, carbon, hydrogen ring transition state.
And by triplet state, you mean that you have two electrons in separate orbitals?
Yes. The electrons are going to be in separate orbitals with the same spin.
Okay, so Logan, if I'm understanding this right, kind of what you were saying is that we've basically now eliminated the possibility of that concerted mechanistic scenario. So we're left with the two hydrogen atom transfer possible mechanisms, one incorporating a barrierless radical rebound, the other incorporating discrete radical intermediates. And the mechanistic experiments that you did kind of were designed to distinguish between those two possibilities.
Certainly the goal of those experiments, and I think there are certain results we could have gotten that would have provided some nice, really solid evidence. But in the same way, KIE experiments can either give you no information or some information. We ended up in a situation where if, for example, with stereo retention experiments, we saw stereo erosion, we would know for sure that it had a discrete radical intermediate, something that could invert.
So could you flesh that out a little bit? So you talk about the stereo retention experiments. What are you actually looking for there?
Yeah, we are starting with a chiral center, and we are then taking that hydrogen away. So what happens next? Do we end up with this discrete radical? If you had a discrete radical that was long-lasting enough, you have then created what you could think about as an sp2 center, which is going to not have chirality. And at that point, you lose the enantiopurity or the enantioenriched nature of that stereo center. When you don't see that erosion, it often indicates that you have no radical intermediate. However, you could also have a radical intermediate that is just so short-lived there is not time for restructuring the orbitals of that carbon or for the rehybridization, because there is a barrier to rehybridization, and if that takes longer than the radical recombination, then you're not guaranteed the information that you want. And that's kind of what we saw here.
I guess what is the information you want?
You want to know what the mechanism is. You want to know if there's a radical intermediate.
Well, it still gives us an idea, right? It's the radical species.
I would say it supports but does not definitively rule out. It's either a very short-lived radical species or a barrierless rebound.
The purpose of these mechanistic experiments was to see the difference in selectivity between the two catalyst systems are coming from any differences in mechanism. And from all these experiments, olefin isomerization, stereo retention, and KIE studies, they all suggest they follow the same mechanism.
So basically, you haven't been able to distinguish between these two mechanisms, but you either have the barrierless radical rebound or a very short-lived radical.
Yes.
And that is what these studies have left you with.
Yes.
Experimentally, absolutely, we have not been able to distinguish between them.
So is the main takeaway then that the difference in selectivity that you see is not a result of different mechanisms?
Exactly.
Okay. So I guess bringing this back out and to finish up, this paper in tandem with a lot of the other previous papers that you guys have published have really been what we've talked about, been going after these selectivity issues in nitrene transfer. What are some of the future challenges that are still present in this field that you guys are thinking about?
I think starting with some of the challenges that are available. Enantioselectivity. There are examples of enantioselective reactions. Each of them come with their own set of limitations. Intermolecularly, nitrene transfer is quite a bit more challenging in a lot of ways. And activating these secondary kinds of bonds in a way that we can do really nicely and a couple other pieces of chemistry can do, albeit not selectively. Intermolecularly, that gets a lot harder unless you're inundating the reaction with substrate or your reactant is something like cyclohexane itself, where there's these 6 sites to react with. A lot of the things that we can do intramolecularly, we can't do intermolecularly. And especially not with a 1-to-1 substrate to nitrene ratio.
If you have an interest in asymmetric catalysis, you probably noticed that how the box ligand scaffold has been well utilized in this chemistry. So probably would wonder, can you use it as in asymmetric catalysis if we're using a chiral ligand? That is certainly one of our next directions, developing a asymmetric variant of this chemistry.
So overall, this paper, I think, was a really nice example of how you designed a catalyst to get the site selectivity that you desired. And so it was really interesting for me to read. It was interesting for all of us to talk about today. And so we just thank you for coming on the podcast. And we're just really glad that you came on today to talk to us about your work and that we can feature some publications that are published here at UW-Madison. If you liked this podcast or this type of podcast, please let us know via social media, and we can provide more examples of papers being published here at Wisconsin.
When you're choosing your catalytic systems, keep silver in mind, and not all that glitters is gold.
And that's our show. Thanks for tuning in to this episode of the Cyclo Edition. For more information on the papers discussed, we have included a selection of the resources we used in our research at the end of the YouTube video. This was our take on a very interesting paper, and we would love to continue the conversation with you. Please comment below the YouTube video and reach out on social media. You can follow the Cyclo Edition on Twitter, where we will post updates about our next episode. You can find the Cyclo Edition wherever you listen to podcasts and on YouTube. If you enjoyed this episode, please like and subscribe. We will provide the paper we will be discussing during the next episode in the description of this podcast, as well as on social media a few days before the next episode is released.